llamando a una reunión por invitación, parece, para tratar el tema de la posibilidad de industria de semiconductores en Perú. Por lo tanto, esta charla resulta muy interesante. Adelante, Marcos.
Thank you, Carlos. Good afternoon. And, my presentation is a brief account of the development of semiconductors. I'm from Federal University of Santa Catarina, Department of Electrical and Electronics Engineering. The topics of my presentation very quickly, and you can find some electronics milestones if you open the book by Professor Jagger. This is a very nice book about microelectronics in general. It has very good summary of the electronics milestones. And I will talk about some of them, okay? And here you see some devices that were used along the history of electronics. You have first vacuum tubes 100 years ago. I suppose that none of you has worked on with vacuum tubes. Maybe you are a very old guy. Okay, so, but some guys still use the people who loves audio, for example, says that, oh, tubes are excellent for audio. I don't know. Tubes, transistors, this is our integrated circuit, small scale integration, very large scale integration, and so on. I'm going to talk about the development of some of these circuits. This is a vacuum diode. What is a vacuum diode? It's a kind of device where there is a heater. The heater heats a cathode, which evaporates electrons, which are attracted or not by a positive plate. So this is the beginning of electronics. This device was discovered or was invented in the beginnings of the 20th century. After this device, there was another one, which is a triode vacuum tube. A grid was introduced, and this grid can modulate the flow of electrons from the cathode to the anode. Then you have possibility to amplify a signal. This signal at the grid can be amplified at the plate of this vacuum tube. Okay, so let's move to this is an anode vacuum tube amplifier. Consists of two vacuum tubes, some transformer coupled signal, and you see here 320 volts. Wow, a huge battery. So this device have a huge dissipation. They are not very useful for computation. You need a lot of processing. So this device are not used, but they were used up to the 1950s something, 1950s. Okay, but now, you know. Oh, this is an old garage in the United States. It's in Palo Alto. This is a garage owned by Bill Hewlett and David Packard. In 1939, they opened this famous company, which is, you know, Hewlett Packard. They produce computers now, printers, and office machines in general. They produced instruments in the old days, but they merged or they sold the instrumentation to another company, which was Agilent, I suppose, and now it's another name, Keysight or something like this. I don't know exactly, but this is one of the most famous companies of the Silicon Valley. They started with vacuum tubes. Oh, this is an audio oscillator, which generates frequencies in the audio range from, say, 20 hertz to something like 20 kilohertz. Okay, this is a schematic diagram, and this is the box of this component, which was the HP 200A. The other one is 200B. They are similar with this frequency range, which provides an output power of 1 watt over a 500 ohms loads. And you see here some very, I don't know if you can recognize this. This is a set of variable capacitors. This is to change the frequency of the oscillator. And you have some tubes here, huge transformers, and this is a very, very heavy equipment, but it was the beginning of this company, and they made success with this kind of instrument. Well, what's this here? This is a patent which was filed in 1926 and was granted in 1920. This is the basic idea of the MOSFET. Two contacts, a very thin layer, and a gate. This patent was granted to Julius Lilienfeld. This is always cited when we are talking about MOSFETs, because the basic idea was conceived in the 1930s, long time ago, almost 100 years ago. Oh, probably you have already seen this picture. This is a computer of the old times. It's the ENIAC, Electronic Numerical Integrator and Computer. It's composed of 17,000 vacuum tubes. A lot of diodes, relays, resistors. Weight, 27 tons, or 27,000 kilograms. You need some trucks to carry this device, okay? You need a lot of air conditioning. You need substitute tubes all the time. They are not reliable. So, but this was a huge computer, and it was built in 1946. It took maybe 8 years until it was decommissioned. Now, this is the same ENIAC, which was designed in probably a little before 1997. You have this performs the same functions of the ENIAC, but look at the dimensions here. This side is 7.4 millimeters, and this size 5.2 millimeters. So it's a very thin die of around 36 square millimeters, and it performs the same or better than the ENIAC. This is a replica, say a replica of the ENIAC, but with a much smaller power, much smaller size, and much better performance. Oh, the dissipation of the ENIAC around 150 kilowatts. You know what's this? Oh, it's a lot of power. And in this case here, you have a few watts of power dissipation, maybe 100,000 less than the ENIAC. I suppose that you know this beautiful picture. It's about the invention of the transistor, the invention of the contact point transistor. These guys are John Bardeen, a physicist, William Shockley, another physicist, and Walter Brattain, a chemist. So this team invented the point contact transistor, not the bipolar, but the basic principles were following by this guy here that described the basic principle of the bipolar transistor. I don't know if you are familiar with this diagram. This is what we call a band diagram of the bipolar transistor. This is the VBE junction. This is the VBC junction, base collector, base emitter junctions. And this picture describes the basic behavior of the bipolar transistor. You decrease you decrease a forward biased base emitter junction and a reverse biased collector base junction. Okay, and this diagram explains how the carriers flow, how the electrons flow through this barrier and go to the collector. Okay, I suppose that you know this. This is one of the equipments that first used the transistor. It still uses tubes here. It's a hearing aid. Okay, it was built in 1952. This is the first portable radio. When I was born, this radio was born also. And it has, you see here, 4 transistors and several inductors, transformers, capacitors, and the battery is around 22 volts. Oh, a huge battery. You know that nowadays this device is power supplied by 3 volts, something like this. But this is a portable radio, and it was very popular in the 50s, and then in the 60s. Okay, this is a place where the Silicon Valley was initiated. Here was the Shockley laboratories, and it was demolished. And they have a board here that says, oh, this was the place where the Silicon Valley was born, something like that. The inventors of the integrated circuit, these 2 guys here, this is Jack Cube. He was an engineer at Texas Instruments, and he was hired, and all the people were on vacation, all his colleagues were on vacation, and he spent 2 or 3 months working very hard in his basic idea of integrating the components in a single piece. And this is one of the basic ideas of the integrated circuit. But the guy who really integrated the circuit in a practical manner was this one here, which is Bob Noyce, or Robert Noyce. Okay, this Robert Noyce died of heart attack in 1950. Jack Cube was awarded the Nobel Prize in 2000 for the invention of the integrated circuit. But when he received the prize, he said that if Noyce were alive here, he would receive the Nobel Prize. But unfortunately, he was not alive. Here's the basic idea of Jack Cube, some schematics. And this is the Bob Noyce patent, which gave origin to the first integrated circuit. The schematics of the cube idea, the cube, this is the associated with the patent by Jack Cube. You have some components, connections. You see, just an integration of components, but the means to reach there was described by Bob Noyce in his patent. Okay, this is Bob Noyce's patent. This is what you see nowadays when you teach integrated circuits, bipolar circuits. You give the students this basic idea of the bipolar transistor, N, P, N, and so on. And here is the integrated circuit. This integrated circuit was integrated in this planar process. Okay, the first integrated transistor. Here is the big, do you know the book by Cedar and Smith? Maybe electronics, the guys who stuff. Okay, this is one of the most interesting figures that describe the behavior of the bipolar transistor. Oh. This was the first monolithic planar integrated circuit in the 1950. This was produced by Fairchild. You listen to a quick story by the creation of Fairchild and Shockley Laboratory. I have a short video to show you some other basic ideas. In 1960, the first MOSFET transistor was demonstrated. 1960. In fact, the patent was filed in 1960 and it was granted in 1963. But here the idea was turning into reality because they had the means to integrate the circuits, the planar process, and they had several means to integrate the circuits. This is another important paper which was published in 1963 by Frank Wanlas and Professor Chetan Shah. And this is the basic idea of the CMOS inverter. This idea was, oh, this is very nice because the previous digital circuits, they spend too much power. And this circuit, when one transistor is on, the other is off, and vice versa. And you don't have a continuous current from this node to this node. So this was a very nice idea. And all the combinational circuits, digital circuits, are derived from this basic cell, just combining series and parallel transistors. You get functions such as NAND, NOR, and etc. So, but the very basic idea of digital circuit, CMOS digital circuit, is given in this picture. Now, something about the Moore's law. Moore was one of the founders of Intel. He founded Intel together with Bob Noyce. So, and in 1965, Moore said that, oh, at each year, the number of components in an integrated circuit will double. But in 1975, he rephrased and said that at each 2 years, the components in an integrated circuit will double. So, but this is a very huge increase by an exponential law. If you have 60 years, 2 to the 30, it's really a huge evolution. Oh, this is the first product by Intel. It was a bipolar static random access memory, 64 bits. It's, well, not, of course, it's not comparable to integrated circuits of today. But anyway, it was an integrated circuit. And this is the first processor for 4 bits. It is the 4004, the first integrated processors launched by Intel. This is the beginning of the processors. Oh, this is I am very fond of this device because when I was a student, this was my computer. This is an analog computer. It solves differential equations, for example. I built a circuit to generate a frequency modulated signal. What's an FM signal? Just an oscillator in which the frequency changes. So it's a second order differential equation in which you change the frequency. That's it. It's was a very nice, but it's not used any longer because you have very powerful computers today. I'm going to show you this short video about the history of electronics.
On, off, simple, the flick of a switch. Yet this simple switch, on, off, is the life force of all digital systems, the pulse of every modern communication and computation device on the planet. In the first half of the 20th century, vacuum tubes, which amplify sound, were a key component in phone systems, radios, and televisions. They could also rapidly switch electrical signals, on, off. Early computers depended on them, from a few hundred to over 50,000 in each machine. But vacuum tubes were prone to failure and generated too much heat. The sheer number required for even simple computation created an obstacle to more powerful computers. December 23, 1947. 3 scientists at Bell Labs demonstrated a radically different amplifier. They started with germanium, a semiconductor that both conducts and insulates electrical currents. By placing gold wires on germanium to manipulate the current, the first crude transistor was born, but it was fragile and not commercially viable. One of the scientists, William Shockley, continued working on his own and developed a robust version. The transistor was ready to move outside the lab. Within 10 years, vacuum tubes were almost completely replaced by transistors.
Dr. William Shockley is one of 3 Americans sharing the Physics Award for research which produced the transistor. Dr. John Bardeen shares the prize. The 3rd colleague is Dr. Walter Hauser Bratton.
William Shockley's brilliant work on transistor technology was trailblazing, but his difficult personality alienated others throughout his career. In 1955, Shockley moved to Mountain View, California, and founded Shockley Semiconductor Laboratory. He rounded up a team of young, top-notch scientists and engineers, but Shockley's style quickly frustrated his new team. In 1957, 8 key employees left to launch Fairchild Semiconductor, less than 2 miles from Shockley Labs. Summer 1958. Engineer Jack Kilby knew his job with Texas Instruments hadn't accrued summer vacation. Instead, he spent his summer wrestling with a problem.
I began to work on what was then called circuit miniaturization.
Complex digital systems at that time required thousands of separate parts, wired and soldered together on printed circuit boards. But they failed often. Kilby believed he could do better.
I began to think about how much you could do with semiconductors and realized that you could make all the circuit elements that you needed.
On September 12th, with upper management watching, Kilby presented his solution. A slice of germanium, wires protruding, attached to an oscilloscope. He flipped a switch. An unending sine wave undulated across the screen. Kilby had taken the first step toward creating the integrated circuit, and with this device, cracked open the portal for modern computing. A stream of innovation followed. While working to improve Fairchild Semiconductor's new transistor design, Jean Erny developed the planar process, covering a silicon wafer with oxide and forming the transistor underneath the protective layer. This improved reliability and made automated manufacturing possible. Director of R&D Robert Noyce made the next leap. He proposed depositing aluminum wires on top of Erny's planar process to interconnect the transistors. This solved a critical limitation of Kilby's approach. A team led by Jay Last combined the work of Noyce and Erny to produce the first practical, easy-to-manufacture family of integrated circuits.
Processes, product, packages, price. Oh yes, and production. Invented here.
At RCA, Frederick Hyman and Stephen Hofstein combined Fairchild's planar process and other innovations to squeeze more transistors onto a chip at lower cost. Silicon ingots sliced into wafers. Wafers etched with transistors. Transistors interconnected into complete circuits. Circuits cut into separate chips. This was the technology that would change the world, and quickly. Driving the explosive growth was Moore's law. In 1965, Gordon Moore observed that the number of transistors on an integrated circuit had doubled every year.
I just took that doubling every year and extrapolated from 60 to 60,000 components for the next 10 years. By putting a lot more stuff in a chip, we were going to make much cheaper electronics.
Today, more than 1 billion transistors can be etched on a circuit chip. All of the Fairchild 8 ultimately left Fairchild to launch their own startups. In 1968, Robert Noyce and Gordon Moore co-founded the Integrated Electronics Corporation. Intel.
Liftoff on Apollo 11.
Autumn 1969. Ted Hoff, a recent Stanford grad and new hire at Intel, was working on a desktop calculator for Japanese client Busicom. Hoff and Stan Mazer proposed a single-chip central processing unit that could be programmed to handle many different tasks, essentially a computer on a chip. Recognizing huge potential, Intel negotiated with Busicom to keep the rights. In 1971, the concept was implemented by Federico Fagin's team, which included Masatoshi Shima. This microprocessor was the forerunner of today's multi-billion-dollar chip industry. The age of the microprocessor had begun. The first microprocessors burst onto the marketplace. These inexpensive digital computers created unprecedented possibilities for new inventions. Chip manufacturing gave Santa Clara County a new identity, Silicon Valley. The population grew 600% as engineers, computer scientists, and high-tech workers swarmed to the new technology mecca in Northern California. Computers, once available only to governments, large corporations, and universities, began appearing on the desks of small companies, in the garages of hobbyists, and into the awareness of the modern world. Smaller, faster, cheaper, and more powerful than ever before, today's microprocessors are an essential element of life, running iPods and airplanes, cameras and power plants, simple toys and space stations.
Okay. All right. Well, this was a short story of the beginning of the integrated circuit age, but it was a nice video. And you have an interesting reference about the history of electronics is the Computer History Museum. It's a site, very nice site, and has a lot of materials about the evolution of electronics, including, of course, computers. These are some pictures of the Jagger's book. This is the evolution of the feature size of dynamic RAMs. And you see that the specific or the feature size has decreased a lot. This dimension here is in micrometers. You are in the nanometer age we are today. And this is the number of transistors on chip. The evolution of computers, a timeline, each decade, you see this 50s, 1950s, one transistor. In the 2020s, 92 billion transistors in a single chip. You see, from one decade to the other, you have something like increase the number of transistors of 20, 50, depends on the computer, it depends on the processor, but the number of transistors at each decade is really impressive how it grows. It's a really exponential growth, and it's according to Moore's law. This is a picture taken in the Intel site, and you have the evolution of the technology. They are not talking about 3 nanometers, but 20 angstroms. Well, you know, angstrom is 1/10 of a nanometer. So you have a, what's the meaning of it? I can't find the meaning of 2 nanometers or 3 nanometers today. In the old times, 90 nanometers was the channel length. Today, it doesn't have a clear meaning. Depends on the manufacturer, depend on the company who is fabricating the chip. This doesn't mean the channel length. It's maybe a little bit arbitrary number. Okay, the types of transistors. This is the old MOSFET, the planar FET. In the more advanced technologies, the FinFET was created. It's a, it's a 3-dimensional topology. And this is the nanowire. Nanowire means it's a nanotransistor like a wire. It's very, very thin. And this is the nanosheet transistor. See, the manufacturers are using the 3rd dimension. This is a prediction of the Moore's law. If Moore's law continues increasing by a factor of 2 for each 2 years, in 2030, 2030, it's predicted that one chip can accommodate 1 trillion transistors. This is the prediction given by the Moore's law, and probably it will happen in 2030. I have here a picture of the top semiconductors producers. 2020 is approximate, and you see here that there is a huge increase of China in the participation of semiconductor production. Taiwan is one of the greatest producers. South Korea, Japan, Europe. You see the percentage of Europe and USA has decreased a lot. Okay, because let's give the production of chips to Asia. Let's keep it there, and we just buy the components, the chips. Oh, this is not. They are very concerned about the production in Asia, because Asia is a very geopolitically sensitive region. There is problem with China and Taiwan. Oh, China says that Taiwan is part of China. So, and what about Europe and the USA? Oh, if something happens there, who will sell integrated circuit to our companies, to automobile companies, to computer companies, and so on? So this is really a huge problem. And you see that the participation of China in the semiconductor production, it was very small, increased here, and it tends to increase And it will take around 30% of the world production. So this is really. Now, what's a foundry? Suppose that you want to design electronic equipment, say for biomedical hospital, for hospitals, for biomedicine. You design your chips, but where do you produce it? Oh, don't go to Intel. They produce chips only for themselves. They don't produce chips if you want to buy. You have to go to a foundry. A foundry is a company that sells services of integration. So you ask the foundry, oh, I need something, then you go to the foundry. You see here that the main foundries are in Asia. Taiwan has most of the foundries, especially this one here, which participates with 54% of the market. So TSMC is also worried about this because it's a Taiwan company and China is always, well, Taiwan is ours. What should they do? So they are opening factories in the United States and in Europe. And there is a factory in Arizona, which will start to produce next year, if my memory doesn't fail. Okay? So this is very big concern of European and American companies. Oh, this shows how the TSMC is the leader of the semiconductor market. Okay. And in order to incentive and invest in local and foreign companies, USA and Europe created two acts, as they call. The American Act is the Chips and Science Act. And just for the Chips Act, it has $53 billion of investment and taxes and I don't know, taxes reduction. And in the case of Europe, this act was created with 43 billion euros just to, again, to bring the manufacturers back to Europe or to create new factories in Europe, new chip factories. What's the importance of chips? Oh, you need chips for everything. For your cell phone, for your computer, for hospitals, for equipment, for cars. There was a shortage of cars in the 2 years or 3 years ago because there were no electronic components for the cars. So everywhere uses chips. Okay. The main suppliers of chips are from Asia. They want to bring back the suppliers to Europe and to the United States. And this is maybe the main reason. Geopolitical instability in East Asia, especially China and Taiwan. Okay. The number of chips fabricated in 2020, 1 trillion, approximately 130 chips per inhabitant of this planet. And for 2030, it's predicted that the mankind will consume 2 trillion chips. And the artificial intelligence will be the most chip demanding area. Okay. The most valuable company today, have you heard of it, is NVIDIA. Yes. Because they are producing chips for artificial intelligence. Yeah. So they are really huge and valuable. Maybe, I don't know how many trillions of dollars. Okay, so these are some references. Thank you for your attention. Suppose we have to finish now, or people are waiting for us. Okay, thank you very much. I can send you the presentation.
Okay. Thank you.
I had some.
I appreciate it.
I will eliminate the instead of. Oh, this is interesting. In the very beginning of integration, the node name was the gate length, but nowadays, look here. This is the transistor length, and the technology is called 2 nanometers or 3 nanometers, the node name, but the real channel gate length is around 15 nanometers. Oh. It's just marketing. Just marketing.
Okay, muchas gracias.
Okay, thank you
Mañana.
guys for attending my presentation.